Welcome back to Programming Fluency. This is section 8.3, Void Pointers and Function Pointers. So far, every pointer you have used was locked to one type. In this video, you will learn how to write code that works for any type using void, star, and function pointers. Let's begin. Welcome back. Your dynamic array from the last section stores integers. Suppose you need the same array for doubles. You would copy the whole thing, change int to double, and rename every function. Need strings too, 3 copies, structs 4, and every bug fix must be applied to every copy. This does not scale. The problem is that C locks every pointer to a specific type, but the growth logic does not care what is stored. In this video, you will meet 2 tools that let you write code for any type. Void star, a generic pointer, and function pointers, which let you pass behavior as an argument. This is the plan for this video. First, void star, a pointer that can hold any address but knows no type. Next, casting to use it. You must cast a void pointer before you can dereference it. Then function pointers, which store the address of a function so you can call through it. After that, callbacks. You pass a function as an argument to customize behavior. Finally, qsort, which sorts any array using a comparison callback. Let's frame the problem. C's type system locks every pointer to a specific type. An int star can only point to integers. A double star can only point to doubles. But there is a catch. Malloc returns memory that has no type at all. It is just bytes. And an algorithm like growing an array or swapping 2 values does not depend on what is stored. The steps are the same whether the elements are integers or structs. So what you need is a pointer that can hold any address. Think of it as a blank envelope. It carries a location, an address, but it does not say what type of thing lives there. That blank envelope is the void pointer. Now the definition. A void pointer, written void star, is a generic pointer that can hold the address of any type. But there is one big restriction. You cannot dereference a void pointer directly. The compiler does not know whether to read 1 byte, 4 bytes, or 8, or how to interpret the bits. So you must cast it to a specific pointer type first. Look at the code. We put the address of an integer x into a void pointer VP, and that conversion is automatic. Writing star VP directly is a compile error, but star, open paren int star close paren VP works. The cast tells the compiler, treat this address as a pointer to int. Then the star reads 4 bytes and reads them as an integer. Void star trades type safety for flexibility. This is the payoff of void star, a generic swap. With fixed types, you would write 1 swap for int, 1 for double, 1 for structs, all the same logic. This single function works for all of them. It takes 2 void pointers and a size, and it does not know or care about the type. It just copies size bytes around, using mempy from string.h mempy of destination, source, in copies in bytes. First it copies a into a temporary buffer, then copies b into a, then copies the temp into b. The caller passes sizeof int or sizeof double to say how many bytes each value takes. This is the core idea of generic programming in C. Forget the type, work with bytes, and let the caller provide the size. Void star lets you handle any data, but what about any behavior? For that you use a function pointer, a variable that holds the address of a function. Think of it as a phone number. It tells the program which function to call, and you can dial a different one at any time. Look at the code. We have add and mul. We declare op with int, open paren star op close paren, open paren int close paren. We point op at add and call op of 3, 4, which gives 7. Then we point op at mul and the same call gives 12. That declaration reads, op is a pointer to a function taking two ints and returning an int. Those parentheses around star op are critical. Without them, int star op of int would declare a function that returns an int star, which is completely different. Now we combine the ideas. A callback is a function pointer passed as an argument to another function. The receiving function calls back to the function you gave it at the right moment. Look at apply. It takes an array, a count, and a transform, which is a typedef for a pointer to a function taking an int and returning an int. Using typedef makes the declaration readable. Inside, for each element, apply calls fn of r of I and stores the result. Apply does not know what transformation to perform. It just calls whatever function you pass. So if you pass doublet, every element doubles. If you pass negate, every element is negated. The same loop handles any int to int transformation. The caller chooses the behavior by choosing the callback. This figure shows the flow. On the left, the caller invokes apply, passing the data, the count, and a function pointer, doublet. In the middle, apply runs its loop, and for each element it calls back to the function it was given. On the right, doublet does its work and returns the result back to apply. Notice the division of labor. The caller supplies both the data and the behavior. Apply supplies only the iteration structure. Neither side needs to know the other's details. And the powerful part, if you change the callback, you change the result without editing apply at all. Now the canonical example, qsort from stdlib.h. It sorts an array of any type, and it combines both ideas from this section. Void star for the type agnostic data, and a function pointer callback for the type specific comparison. In the signature, base is a pointer to the first element, nmem is the number of elements, size is the size of each element in bytes, and compare is the comparison function. Qsort handles the whole sorting algorithm. You just provide the comparison. The comparator returns a sign, not just 0 or 1. A negative result means it comes before B. 0 means A and B are equal. And a positive result means it comes after B. Getting this convention wrong is a common bug. Let's sort integers. The comparison function compare ints receives two const void pointers because qsort does not know the element type. Inside, we cast each one to const int star and dereference it to get the actual integer. Then we compare, returning -1 if it is less than b, +1 if it is greater, and 0 if they are equal. Then we call qsort, passing the array, the count 5, sizeof int, and our comparison function. The output is sorted, 3, 8, 17, 42, 99. One warning. You might be tempted to write return ia-ib as a shortcut. Do not. If ia is a huge positive and ib is negative, the subtraction can overflow and give the wrong sign. The if-else pattern is always safe. Sorting strings needs careful attention. The array is an array of char pointers, so each element is a char star. When qsort passes an element to your comparison function, it passes the address of one char star in the array. That is a pointer to a pointer, a char double star. So inside the comparator, you cast the const char double star and dereference once to get the actual string pointer. Then strcmp compares the strings alphabetically. The figure traces this. Level 0 is the array of pointers. Qsort passes the address of an element. Level 1 is the parameter, a void pointer that is really a char double star, so you cast and dereference once. Level 2 is the actual string data. If you cast a char star instead of char double star, you would compare the pointer bytes as characters, which is garbage. Here qsort sorts an array of structs, and it is actually simpler than the string case. We have two comparators and this one goes first. By score casts each void pointer to a const student pointer, then compares the score fields, returning a sign. To sort by score, you call qsort with by score. The second comparator by name casts the same way and calls strcmp on the name fields. To sort by name, you call qsort with by name. Same array, two different orderings just by passing a different comparator. And notice the cast is only a single level here, const student pointer, not a double pointer. That is because the array stores student values directly, so each void pointer points straight at a student. In the string case, the array stored pointers, which is why that one needed the extra level of indirection. Let's cover two common bugs. First, dereferencing a void pointer directly. Here we put the address of x into VP, then write int val equals star VP. The compiler refuses. A void pointer has no associated type, so the compiler does not know how many bytes to read or how to read them. Remember, void means no type. A void pointer is just an address with no size information attached. The fix is to cast to the correct pointer type first. Int val equals star, open paren int star close paren, VP. Now the compiler reads 4 bytes and treats them as an int. The second bug, the wrong cast in a qsort comparator for strings. Here the programmer casts the void pointer to const char star, then called strcmp. But remember, the array holds char star values, and qsort passes the address of each element, which is a char double star. By casting to just char star, you treat the address of a pointer as if it were the start of a string. So strcmp compares the raw bytes of the pointer values, not the actual strings. The sort produces garbage, and strcmp may read past valid memory and crash. The fix is to cast to the right level of indirection. Const char star sa equals star, open paren const char double star close paren. A dereference wants to get the real string pointer. Let's recap. Void star and function pointers are how C writes generic, reusable code. A void star holds any address, but you cannot dereference it until you cast it to a concrete pointer type. To walk a generic array, cast a char star and add I times size, doing byte-level arithmetic. A function pointer stores the address of a function. The declaration reads, fp points to a function taking 2 ints and returning an int. A callback passes behavior as an argument, and the generic algorithm calls it back at the right moment. And qsort sorts any array, using a comparator that returns a sign, negative, 0, or positive, not just 0 or 1. Next, you will combine these tools to build a linked list, nodes connected by pointers, and you will meet the double pointer, node double star, that lets a function change the caller's head.